We would now like to discuss drag forces in a fluid. Now remember that fluids can be both a liquid or air. And drag forces are actually quite complicated depending on a lot of factors. If we had an object falling in a fluid, the drag forces can depend on both the properties of the object, and in that case, it might be the speed or the size or the shape of the object. And it also can depend on the properties of the fluid. It can depend on the density of the fluid. It can depend on a property that measures the resistance of the fluid, something which we'll refer to as viscosity, and also a property about the compressibility of the fluid. So in general, this is quite complicated. And this is done empirically. There's a few very special cases that we'll discuss that can be solved exactly. Now, let's begin our modeling by considering what we call air drag. Now, in air drag, objects that are moving, and we'll consider objects that are moving rapidly. So our objects are moving very fast. Now, in that case, we can make a rough model of the air drag as follows. The magnitude of this force is going to be proportional to the speed squared. There'll be a factor where it's the cross-sectional area that the object presents in the motion perpendicular to the plane of motion. It can depend on the density of the air. And traditionally, there are a couple of coefficients in here that are dimensionless that are empirically determined by the shape of the object, and that's called the drag coefficient. And in fact, there's also a factor 1/2 in the way this law is traditionally written. So what we have here is a resistive force which is proportional to the speed squared and depends on the properties of the air, the density of the air, and some physical properties of the object itself. Now, this drag coefficient, we can have a table that can represent that, and you can see here that for a variety of different shapes, the drag coefficient is somewhere on the order of 1. So this is an example of what we refer to as air drag. When we drop objects in a fluid at very slow speeds, we have a different effect than what we talked about air drag. For example, if we drop a marble in molasses and drop the same marble in water, we see a very different motion. And that depends on a property of the fluid, which we'll refer to as viscosity. Now, we'll denote a coefficient of viscosity by the symbol n, eta. Now, when we drop an object in a fluid, that the drag force in magnitude will be proportional to both viscosity, will be proportional to the speed, and it will be proportional to the viscosity. And now, for very special cases, so for the special case, which is a sphere of radius r, if you study fluid dynamics, we can get an exact solution for this drag force, and we'll describe that as it's going to be opposite the direction of the velocity, so there's a minus sign. There turns out to be some coefficients, 6 pi times the viscosity of the fluid times the radius of the sphere. And this particular law, which we'll known as Stokes' law, is exactly applicable to the motion of a sphere. Now, in fact, by experimental measurement, this is a method for determining eta experimentally by dropping objects, spheres, in various different media with different viscosities. So we can use this to experimentally determine the viscosity of the medium. And what's important to realize, too, is that this is applicable to many different examples. We'd like to consider velocity-dependent resistive forces. So let's imagine a situation where we have an object, and it's falling in a gravitational field, so we have a gravitational force, And this object is like a marble falling in a vat of oil. And there is a velocity-dependent resistive force that is acting on this object. And let's again choose a positive direction down. And now for objects that are moving very slowly in a fluid, let's make a model for our velocity-dependent resistive force. We'll assume that the resistive force is proportional to the velocity, it's opposing the direction of motion, and we'll put a coefficient alpha in front. And this is our model for velocity-dependent resistive forces for objects that are moving very slowly. For our case, let's consider the units of the coefficient alpha. So the units of alpha have the units of force divided by velocity. So the units of force are, we have the units of force divided by the units of velocity, and that gives us kilogram meter per second squared, divided by the units of velocity, which are velocity per second. And so we see that the coefficient of alpha has the units of kilogram per inverse second. Now what we'd like to do is apply Newton's second law. So let's analyze the forces and get the equation of motion for this object falling in a viscous medium with a resistive force. In the j-hat direction, we have the gravitational force, and we have our resistive friction force, which we're writing Vy as the y component of the velocity, and that's equal to m times dvy dt. Now notice that the acceleration we're not treating as a constant, it's the derivative of the velocity. This leads us to our differential equation, which is written as dy dt. I'll divide through by m, g minus alpha over m vy. Now this is a linear in velocity, first order differential equation with a constant term in here, which is called inhomogeneous linear first order differential equation. We shall solve this like we did with our other equations by separation of variables. So what we do is we bring the velocity terms to one side and the time terms to the other side. And now we can integrate both sides directly. But before I integrate this side, I'd like to rewrite it by writing it as dvy, and I'd like to pull out a minus alpha over m. And this term here becomes minus mg over alpha. Why did I do this? For the integration, it just makes my natural logarithm integral look a little bit easier. And over here, I have dt. Now what I want to do is integrate, and we're going to integrate from some initial velocity, which we're going to take to be 0. We're going to drop this, let this object be released from rest, and we're going to integrate to some final speed vy of t. Over here, let's just call our integration variable t prime, and we integrate t prime from 0 to some time t. So this is our variable, and the velocity is a function of time. Now, doing this integral, first off, this constant term comes out. So we have 1 over minus alpha over m. And the integral is just a natural log integral of vy minus mg over alpha. And we have to divide that. In the lower limit, vy is 0, and we have just minus mg over alpha. And this side is very simply t. Now, we can rewrite this equation by bringing the m over alpha to the other side. And we have log of vy minus mg alpha over minus mg alpha equals minus alpha mt. Now recall that e to the log of any quantity x is equal to x. So if I exponentiate both sides, I get vy minus mg over alpha divided by minus mg alpha is equal to the exponential e to the minus alpha mt. Now the last step is simply to bring this over to there, multiply, and do a little bit of algebra. And so I get that the velocity as a function of y is equal to mg alpha times 1 minus e to the minus alpha mt. Now, there's a few interesting things here that we want to look at. Suppose we define this exponential, e to the minus alpha mt, as equal to e to the minus t over tau. where tau is m over alpha. The units of tau, when we look at the units, it has the units of mass, which is kilograms, over the units of alpha, which we worked out before. So we have kilograms over kilogram inverse second. That gives us units of seconds. And that's what we expect because t, seconds over seconds, gives us dimensionless quantity for the exponential. Now, the last thing we'd like to look at is let's just see what happens when we plot this. Well, if we're plotting Vy as a function of t, we start off at 0, and we're going to reach some terminal quantity, Vy terminal, which is when we have a graph like that. And we can see what that terminal speed is. When we set t equal to infinity, e to the minus infinity is 0. And so this terminal speed is equal to just this coefficient, mg over alpha. And that's the terminal speed. Now, notice that as a check for what we did, we can come back to our differential equation. And what does terminal speed mean? Notice that when you get to this limit as t approaches infinity, the slope of the velocity curve is 0. And that's really the statement over here that Vy terminal is when the velocity is no longer changing in time. You can see it graphically. And this is the statement, when we go back to Newton's second law, that there's acceleration is 0, so the sum of the forces at terminal speed are 0. The resistive force is equal to the gravitational force. And so from this equation here, as a check, we can see that Vy terminal equals mg over alpha, which checks with our calculation. And so we have confidence that we analyze this correctly. And that gives us our motion. One last thing that's quite interesting. Notice that the terminal speed depends on mass. This coefficient alpha is only a function of the properties of the object, the size, the shape, the geometric properties of the object, not how dense it is. So if you had two objects, like two balls, same radius, but one was denser than the other, then the other one mass would be heavier, and the terminal speed would be greater. So what we see is that two identical objects, one heavier than the other, the heavier object reaches a faster terminal speed than the lighter object, which explains a well-observed phenomenon. Now we're going to analyze a more complicated example of drag forces, where we have an object falling free in a gravitational field with gravity. We have a resistive force. And this is an object in air. And so our model will be for the resistive force that it's going to be proportional to the velocity squared. Now, to get its direction right, opposing the motion, j hat. So this will turn out to be a more complicated analysis. But first, again, let's think about the units of our coefficient beta. It has the units of force divided by velocity squared. So we write the units of force, kilogram meters per second squared, and the units of velocity squared, meters squared per second squared. And so we see that we have units of kilogram per meter for our coefficient beta. Now, we'll apply, as usual, Newton's second law, F equals ma. To get our equation of motion, we're looking at the j direction. And our forces are gravity minus the velocity squared resistive drag force. And that's equal to the derivative of the velocity dv dt. In this example, it's a one-dimensional motion, so I'm dropping any mention of our y direction for simplicity. Now we can rewrite this equation as dv dt. Let's divide through by m is g minus beta over m v squared. And this is a linear, it's a first-order differential equation, dv dt. It's a nonlinear equation because the velocity term appears here as a square, and there's a constant term. But we can still apply our technique of separation of variables, and so we'll rewrite this equation as dv dt. We'll separate out the dv's and the t's. So we have dv times g minus beta over mv squared is equal to dt. Now, I'm going to do two things just to clean this up for algebra a little bit later. I'm going to multiply both sides by a minus sign, and I'm going to pull the g out. So I have 1 minus beta over mg v squared. And on the other side, I have minus dt. And now I can get this equation in the form that I'd like to integrate, which is minus dv times 1 minus beta over mg v squared equals minus g dt. Now, the trouble here is this integral is a little bit complicated, so I'd like to make a change of variables. And my change of variables will be u equals the square root of beta mg times v. And that implies that du is beta mg dv. And the limits, if we start our object at rest, so if u naught equals 0, then because v naught equals 0, that's our first limit. Now, we have to be a little bit careful, because if we drop this object at rest, initially it will be moving very slowly. And so our resistive model doesn't actually apply. However, we're going to neglect that effect, even though if we were to do a more complicated analysis, we would have to change our model as the object is falling. So it would be a multi-stage motion, first at the beginning with our only velocity-dependent resistance, and then as it gets some initial speed and it's going faster, we change our model. That's why the actual problem can be quite complicated, but we're just trying to keep things simple here. And then u at t is square root of beta mg v of t. And then with this change of variables, my integration, remember I have a dv, so I have to multiply the left side by mg over beta, and I'm integrating with a minus sign du times 1 minus u squared from 0 to this final value u of t. And over here, I'm just integrating minus g dt. Now, again, for simplicity, I'm going to bring this term, the beta over mg, over to the other side. So I'll use the magic of our light board by just erasing that and bringing it to the other side, which makes my life a little easier. And now, this integral can be done by the method of integration by parts. It's a nice problem in calculus. And you can verify for yourself that the result is 1/2 natural log of 1 plus u over 1 minus u, evaluated at our limits. And over here, I have minus g square root of beta over mg. Now, once again, for a little bit of simplicity, I'm going to bring the 2 over to the other side. And now I evaluate my limits. Now recall that when you have a minus log, we're flipping because log of b over a equals minus log over ab. So when I put out my limits in, I have natural log of, now remember, what are our limits? We have 1, I'm flipping, minus u is beta mg times v of t. And I have the 1 plus beta mg v of t. And that's equal to minus 2g square root of beta mg. Now, again, we'll use the fact that e to the log of x is x. And so if I exponentiate both sides, I end up with 1 minus square root of beta mg v of t over 1 plus square root of beta mg v of t is equal to exponential minus 2g beta mg times t. And we'll just remove that. OK, now this is a little bit of algebra. I want to solve for v of t. If I bring this side over to there, I'll just do that to make the first step a little simpler to see. So we have 1 minus square root of beta mg v of t equals 1 plus square root of beta over mg v of t times e to the minus this factor 2g square root of beta mg t. Now, this is a lot of stuff to carry around. I'd like to introduce a constant here, tau, which I'm going to define to be square root of mg beta 1 over 2g. And so this whole term is going to just be e to the minus tau. It's a nice example for you to work out that the units of tau are the units of seconds. And that's a little exercise to work out. Now, I just have to collect my terms. And what I'll do is I'll collect the t terms on the right and the terms that don't have vt on the left. So I have 1 minus e to the minus t over tau on the left is equal to 1 plus e to the minus t over tau on the right times beta mg v of t. And so I get my solution, v of t equals the square root of mg over beta times 1 minus e to the minus t over tau over 1 plus e to the minus t over tau. Well, it's not a simple solution at all. But let's examine, when you have a case like this, again, it would be a nice exercise to graph this out. But right now, we're going to consider the limit as t goes to infinity. And remember that e minus t over t goes to 0 when t goes to infinity. So we just have 1 over 1. And what we get as t goes to infinity is the quantity mg over beta. And this is what we call the terminal velocity. Now, what does terminal velocity mean? Well, when an object is falling and there's a resistive force, as the object falls faster and faster, the resistive force gets greater and greater until, if we go back to Newton's second law and look at it, as the v gets faster and faster, eventually these two terms are equal. And when these two terms are equal, that's the statement that the right-hand side has to be 0. So what we mean by terminal velocity is the velocity is no longer changing in time. And then we can immediately check our work by going to Newton's second law and see what that case is if we set this quantity equal to 0. In other words, when we set mg minus beta v squared terminal equal to 0, we can solve for v terminal, and we get square root of mg divided by beta. And that agrees with our lengthy calculation. So we think we're on the right track.